Good morning everyone. Welcome to this video tutorial on a finite element analysis, a practical approach using ANSYS. So myself, I am Shankar, Assistant Professor from Mechanical Engineering here at the College of Engineering, Madurai. So before starting any analysis, I would always start with the steps involved in any FEA analysis using any FEA software. So it can be basically categorized into three steps: pre-processing, processing and post-processing. So the majority of our work lies in this stage, pre-processing, where you have to define the problem, select your element, define the material properties and section properties if required, model the problem, then mesh the problem, and finally decide the boundary conditions. Right? Once this is all done, solution, this is where computer comes into play, and finally post-processing, you'll be able to review the results, provide suitable suggestions and recommendations, and prepare your report. So this is some of the work that we have to do. The majority of the work for analysis has to be done in this pre-processing. So this is a series of video tutorial. We have already completed the structural analysis, so the link can be found in my YouTube channel, right? And we have also completed the thermal analysis. Now we are moving to the dynamic analysis, and in this video tutorial we'll be seeing about the modal frequency analysis for a beam, right? So before starting to see what is this modal frequency analysis and taking an example and solving it in ANSYS, let us try to understand some basics on this modal frequency analysis. Basically, we are going to do some dynamic analysis. So the difference between the static analysis and dynamic analysis is that in static analysis, we'll consider the forces to be static and the response of the system to be static. That is, it does not depend on any time. So time independent process is static analysis. Whereas in here, dynamic analysis will consider a particular time, that is the body is in motion. So that is where we are going to do the dynamic analysis. In dynamic analysis, we are going to concentrate on one particular area called as vibration. So that is where these two exercises, modal frequency and harmonic frequency response analysis, comes into play. So we are not going to see any other dynamic analysis like say a car is traveling at some kilometer per hour, or a bullet is traveling and hitting a plate, right? These are some of the dynamic analysis, but we are not going to see all those things. We'll be seeing the dynamic analysis particularly related to vibration, right? So before starting to see this modal frequency analysis, let us get some introduction about the vibrations. Okay, so what is a vibration? So what are the types of vibration? Is nothing but the definition of vibration can be said that a particular periodic oscillation about an equilibrium point, right? So say for example, when you drop something, or say for a coin onto the ground, and you can feel the vibrations, right? And when you are traveling in a car or a bike or a train or in any vehicles, you can feel the vibrations for yourself, right? So vibrations is everywhere in and around us, and one of the important vibrations that is present within ourselves is our heart, which continuously pumps the blood and it beats for 72 beats per minute in a particular rhythm, right? So it is a periodic oscillation, right? Like this, I can tell you lots of examples related to vibration. So vibrations can be categorized into periodic or random vibrations. So periodic vibration, you will have a uniform oscillation about a point, and the mathematical graph for the particular vibration can be simulated equivalent to a sine wave, right? A sine wave will be the output displacement for a periodic oscillation. Whereas in case of a random vibrations, you can't find this beautiful sine wave. You'll find some irregular random stretch of curves which will represent the vibration. So we are not going to see about random vibration. We will see about a beautiful sine wave which is represents a periodic vibration, right? Some of the terms involved in this vibration is that amplitude. So the maximum level up to which you get the vibration is the amplitude. So from the baseline to the topmost thing is the amplitude. Along this graph is along the x-axis you have the time, and along the y-axis you have the amplitude, that is the displacement from the mean position, right? So a sine wave starting at a mean position, then crossing a mean position, then going on to the other side, and again coming to the mean position. So this can be considered to be one cycle, right? So the frequency is nothing but inverse of time period, which is number of cycles per second. So say for example, this one cycle takes 1 second to complete, then the frequency is 1 cycle per second, or the popular unit for frequency is hertz, right? Okay, so this is a basic introduction about vibration. So based on the types of vibration, we can classify into free, forced, and damped vibrations. So vibration is a motion basically, right? And any motion requires a force to be required to be set up, right? In order to have a motion, you need to have a force, right? Free vibration is where you'll not have any external force, only the initial exciting or the displacement force. So say for example, you take a string, you initially give it a pull and or push, and then you come away, but the swing keeps on moving until due to the air friction it comes to a particular stopping position, right? So in that particular case, you initially give a push and then you come away, but the swing keeps on swinging, right? So that's the case of a free vibration. Whereas in case of a forced vibration, you stand behind the swing and you keep on pushing each time the swing comes to you, and you can find that swing will not stop at any point because you are continuously exciting the swing and it keeps on moving, right? And finally, a damped vibration is where the amplitude diminishes with time. Like in case of a swing, when you initially give it a push and you come away, it will not keep on swinging forever because the air surrounding it will create a particular friction, and that air resistance is called as damping, and which will stop the swing at a particular point. And one more example, say if take a ball and if you drop it from a particular height onto a tub with water, the air falls with the velocity, and the air until it touches the water, the air surrounding the ball will reduce its velocity. Once it touches the water, it keeps on moving and its velocity drops drastically because the fluid viscosity and density stops the ball from moving further deep ahead. So one is the air resistance, another one is the water resistance. So combined together, we can call it as fluid resistance. So the fluid resistance is called by a special name called as damping, right? So these are the types of vibration based on the force that excites the vibration or stops the vibration, right? Okay. And there is one more category of vibration, right? Where based on the direction of vibration, you can classify into longitudinal, transverse, and torsional. Like longitudinal vibration, the axis of the vibration is parallel to the axis of the object, whereas in transverse vibration, the axis of motion of vibration is perpendicular to the axis of the object, and torsional vibration, you have a twist along the axis, you have a rotation about the particular axis of the object, right? So these are the basic categories of vibration based on their axis of movement. And so a small derivation on finding the natural frequency of vibration. So free longitudinal vibration, considering a spring mass system. So these are the derivation which you can find in any book. I'm not going to detail it in a very detailed manner. I'm not going to tell it in a detailed manner. You can find it in any vibration book, or you may have already studied. Okay. So the final formula comes down to this: omega equal to root of S by m. And I can rewrite it as omega equal to root of S by m or root of g by del, where g is the acceleration due to gravity and del is the deflection due to the particular mass. So this frequency is called as angular circular frequency. It is in radian per second, but the unit of frequency will be in hertz. So in order to convert this, we know that omega is equal to 2 pi n, and n can be written as 1 by time period. So omega equal to 2 pi by time period. So if I rewrite this, I will get time period equal to 2 pi by omega, which is 1 by frequency. And if I rewrite this equation, I'll get frequency equal to 1 by 2 pi into root of g by del. So this is the ultimate formula. So this 1 by 2 pi into root of g by del is the ultimate formula for finding the natural frequency of any given object. So now what is the natural frequency, right? Say for example, when you drop any object, when you give a initiating force to any object, each object vibrates at its own frequency, which is a constant value, which is called as the natural frequency of the object. Let me give you an example. When you drop a coin from a height of 1 meter, it vibrates actually. You can hear a sound of the coin vibrating along in the floor. Once it touches the floor, you'll get a sound. So say for example, that frequency is the natural frequency of the coin, right? Now, if you drop the same coin from a height of 4 meters, you will hear the sound even more higher. It doesn't mean that the frequency is changing. It means that the amplitude of vibration, that is the amount of displacement is higher, but the frequency still remains the same whatsoever height you drop the coin from. It may be 2 meters or 10 meters or 20 meters. Even if you drop it from 20 meters, the loudness with which you hear the vibration increases, which means the amplitude of vibration increases, but the frequency of vibration still remains the same. So frequency of vibration is a property of a system. like the Young's modulus, density, Poisson's ratio, right? These are some of the properties of a particular given object, right? Like the geometrical parameter, like the cross section, like the length of the object. So these are all constant values. Similar to that, the natural frequency of a particular object is also a constant value, right? You can calculate the natural frequency of object using this formula 1 by 2 pi into root of g by del. For transverse vibration, this del can be replaced using the formula PL by AE. Whereas for transverse vibration, so consider a beam, a cantilever beam with an endpoint load, or a simply supported with center point load, or with a uniform UDL, or fixed beam with the center point load. You have the deflection values as shown in the formulas. And if you substitute these deflection values in this formula, you get the natural frequencies for transverse vibration in all these cases, right? So this is the introduction about the natural frequency of the given object. Now I'm going to just rewrite this formula, right? This formula 1 by 2 pi into root of g by del for the natural frequency, right? So here I have omega equal to root of k by m, which is k is the stiffness, m is the mass, and is equal to root of g by del. So consider this 1 by 2 pi into root of g by del. For beams, the deflection is transverse deflection, so hence the vibration is going to be a transverse vibration. So for any beam, the formula for deflection is del equal to WLQ by CEA. So consider this beam. Let be a cantilever beam with endpoint load. It is WLQ by 3A. Whereas simply supported beam is WLQ by 48A. So for any beam, you can find the formula WLQ by EA remains the same. Only the constant values changes for each and every case. Here you have UDL pi WL power 4 divided by 384A. Here W is W per unit length. So once you cancel one length, you'll get again you'll again get the WLQ by EA, which is again similar to the above cases. Only this initial number values keeps on changing for each and every case, right? So hence I can generally write it as WLQ by CEA, where C is the constant number, which depends on the particular case in which I am solving. So if I substitute this value in this formula del here, I'll get something like this. If I simplify this, I'll get root of C by 2 pi into root of GEA divided by WL cube. We know that W equal to mass into acceleration due to gravity, and root of C by 2 pi, it is a constant. I can again rewrite it as capital C, right? And if I substitute these two values, two functions in the above equation, I'll get something like this, right? So natural frequency F1 is equal to C into root of EA divided by ML cube, right? Here the unit of frequency is hertz or cycle per second. In order to get the frequency in the unit of hertz or cycle per second, you need to substitute the Young's modulus in Newton per meter squared, moment of inertia in meter per 4, length in meter, and mass in kg. You can't change these values. You cannot substitute it as mm, and you can and expect the same hertz or cycle per second as the unit for frequency. Let me explain you why. Let me substitute the unit system of all this in the above equation. So Newton per meter squared for the E, and meter per 4 for I, and mass is in denominator, so 1 by kg, and L cube is meter, so 1 by meter cube. So if I cancel this all out, finally I will get as kg meter again, in the denominator. This Newton can be rewritten as kg meter per second squared, and denominator I will have a kg meter. I will cancel this, will get cancelled, and the root of 1 by a squared is 1 by second, which is hertz, right? So C has no unit, so it is a constant. So the unit of frequency will be hertz. It is compulsory that in vibration that all the unit has to be in meter and not in any other unit, say mm or centimeter or kilometer or whatsoever unit. So in this formula, you should always substitute all the units in meter, and the force unit should be in Newton, and the mass unit should be in kg. This unit system must be retained for doing the theoretical calculation, which is very much important. If not, let me tell you what will happen. So what if I substitute the length unit in mm? So if you substitute the E in Newton per m square, mass in kg, I in mm power 4, length in mm, and if you cancel all these things, so the Newton is always kg meter per second square. You can't rewrite the Newton as kg mm per second square, right? So the Newton is always kg meter per second square. In the denominator, you will have kg mm. So only this kg will cancel. I can't cancel this meter and this mm, right? And here I cannot cancel meter and mm, and hence this is the reason I have to use only meter in the above formula for natural frequency, right? Or else you can also do one thing. So in order to convert this meter into mm, I have to multiply 1000, and only then I can cancel the mm. So if you substitute in mm, then they multiply root 1000 to the final answer, right? So instead of doing this thing, multiplying the root 1000 to the final answer, you can simply substitute all the values in meter, that is all the unit system in SI units, and you can directly get the frequency in hertz, right? So this is one thing which I wanted to tell you, very much important. Now let me get on to my problem and let me show you how to solve. So I have this is a problem that I have taken, and so of a 1 meter length beam of cross section 50 mm cross 50 mm, Young's modulus 200 gigapascal, Poisson's ratio 0.3, density is 7,800 kg per meter cube. So if I substitute all this in this formula, root of EI by ml cube, and I'll get root of EI by ml cube will be 73.0881628, and it will be multiplied with this constant value. So for each and every case, this C value gets changes, and I can multiply the corresponding C for a particular problem, and I'll get the natural frequency for each and every given system. So this is a beam. I have not specified it whether it's a cantilever beam or simply supported beam or a fixed beam. I have not specified anything. I just had taken the length and cross section data of the beam. Depending on whether it is a cantilever, whether it's a simply supported or a fixed beam, this C value changes. So this C value can be found out from this table column, natural frequency constants of beams. So I have different boundary conditions: cantilever, simply supported, fixed, free ends, fixed and hinged free. Right? Here in the bottom also you can find the same formula which I rewritten above, shown you above. Right? So use this formula, root of C into root of EA by ml cube. And this formula differs from this formula by the fact that W is substituted as M into G, and here W is in weight per unit length of the beam. So I can cancel one length here. So this L power 4 will become L cube, and this W can be rewritten as M into G, and I can cancel the G. So this formula again changes to EI divided by M into L cube, which is same as my formula, right? So it's nothing wrong that if you use this formula or if you use this formula. But be careful in using this formula. Here weight is in unit length. You have to cancel one length to convert this to L cube, right? Okay. Right. Now this constant C can be found out for different boundary conditions here. Say for cantilever beam, for first 5 modes of natural frequencies, you can have this constant C values here, right? So what do you mean by different modes of frequencies, which can be clearly seen by the image that has been shown in each and every case. So if the beam deflects like this, right, if it crosses the mean position at only one point, this is the first mode. Here you can see this one point here and one point here does not move anywhere. It is still remains in the mean position. So this is the second mode. Here you can find this. Here I have this fixed point. I have one more point here and I have one more point here. 3 points does not move, and this is the third mode. And in the fourth mode, you'll have 4 points which always remains at the mean position whatsoever the vibration is. And in the fifth mode, you'll have 5 points which always remains at the mean position whatsoever the vibration is, right? So this is the first 5 modes, right? Similarly, you'll have n number of modes. You have infinite number of modes for any given object, right? So natural frequency is a constant, but this constant value, there are lots of constant value for a particular case, right? If you take even a cantilever, only the first 5 mode is given. You can calculate the 6th mode or 600th mode or 6000th mode, but it is impossible to achieve the 6000th mode in an experimental real world scenario, right? So that is why they have stopped only up to 5 modes, right? So using this, you'll be able to substitute the values and calculate the natural frequency, which I have done here. So I have calculated for all the 6 boundary conditions, whereas I'm going to show you only cantilever, simply supported and fixed in ANSYS. I'm not going to show you these 3 things. So I have calculated the theoretical natural frequencies for cantilever beam, simply supported and fixed beam. For in all the 3 cases, my material property and my cross-sectional property, my length property remains the same. This is the same for each and every case. Only the boundary condition is cantilever, simply supported and fixed in 3 of these cases. And the first 5 modes for the corresponding cantilever, simply supported and fixed beam have been calculated here, right? Let me verify this with the help of a ANSYS value, right? Now let me get on to the ANSYS. Okay. Now, so as I already told you, right? Okay, this is my problem. Young's modulus, Poisson's ratio, and density. Length is 1 meter. Cross section is 50 mm. And if you remember, the unit system should always be in meter. Hence, even while solving an ANSYS, you should always keep the unit system in a SI unit. Do not change it to mm or centimeter or whatsoever given in the question. Change all the SI unit to meter. All the dimensional unit to SI unit, that is meter for length, and the force unit is Newton, and the density is in kg. The mass unit is in kg per kg, right? So be sure that you have all these units in SI unit, right? So my problem is determine the first 50. So I'm going to calculate 50 natural frequencies. So these natural frequencies called as the modal frequencies for the above beam, and only the configuration is going to change, which is cantilever, simply supported and fixed, and all the other parameters are going to remain the same. Even though if I calculate the 50 natural frequencies, I can only compare the first 5 natural frequency with that of the theoretical calculation, because I don't have the constant C value for more than 5 frequencies. So in order to compare, I will compare only the 5 frequencies, right? Okay. Now the first step is problem definition, which have been completed. The second step is element selection. As this is a beam problem, I'm going to select beam 2 node 188 element, right? And the properties are given, which you can read it and find out. And the third is material property, which is Young's modulus, Poisson distribution, and density. And the important note is the unit system has to be in SI units only. That is, force unit should be in Newton, length unit in meter, and the mass unit should be in kg, right? And similarly, for the cross-section properties, I have to give a square cross-section, and which is available in beam bound sections. But here also, I should keep the unit system in mind. That is, the length unit should be a meter, right? Okay. Once the material property and section properties are added, I have to model the problem. So modeling is very much simple. So here also use the unit of meter, 1 meter length. Don't give 1000 mm, right? Be sure in that. Once the modeling is completed, I have to mesh the problem. So here the mesh attribute, which is not required. If you have multiple materials or multiple cross section, you need to go for mesh attributes, or else you do not need to go for any mesh attributes. And directly I can divide the problem into number of elements, say 100 elements, and I can mesh the problem, and I can convert it into elements, right? Okay, so this is the stage where ordinary problem gets converted into a FEA problem, right? Okay, so once this is done, I have to go for boundary conditions. So here I have 3 boundary conditions. So first, initially I have to analyze the problem as cantilever beam. Then I will analyze the problem as simply supported beam. Then I will analyze the problem as fixed beam. Each case, the boundary condition differs. In cantilever beam, only one end is fixed, which means all degree of freedom. That is, 3 translation is 0 and the 3 rotation is 0. In simply supported beam, 3 translations are 0 and the 2 rotations are 0, and the out of plane rotation should be kept as free. That is, the rotation about dz should be free. And fixed, both ends are fixed, and both the translation and rotation at the both the ends should be 0. So I am going to solve pretty much 3 problems separately. One as cantilever beam, and the other as simply supported beam, the other as fixed beam, right? And so one more thing that you have to do here, which we have not done earlier, is that you have to change the analysis type. So far the analysis type is static, so that we have not changed it to anything. Now we have to change the analysis type to modal, and under the analysis option you have to determine how many number of frequencies to be calculated by ANSYS, right? You can calculate n number of frequencies, but as I already told you in the problem definition, I am going to see only the first 50 natural frequencies using ANSYS, but I am going to compare only the first 5 natural frequencies with the theoretical calculation. Now let us see how to solve this problem in ANSYS. So now first I will solve this problem as a cantilever beam, right? Okay, let me minimize this. Let me go to start menu. Let me go to ANSYS 19 here, and yeah, here I have mechanical APDL 19.0. Okay, so once the ANSYS APDL menu opens, so go to preferences. So this is a structural problem, structural, okay, and okay. Now go to preprocessor, element type, add, edit or delete, add, and beam 2 node 188, click on OK and close. Next go to material properties, add the material, structural, linear, elastic, isotropic. My material is Young's modulus 2e power now Newton per meter squared. So as I already told you, I'll give all the units in SI unit, right? And I also have to add the density to calculate the mass, right? So the density is 7800 kg per meter cube. So it is an SI unit. I have added it SI unit. Okay, close. Next, come to sections, beam, common sections, and 0.05 meters. That is 50 mm and 0.05 meters, right? Click on OK. Now modeling the problem. Great. This is similar to what we have seen in our beam, calculating the deflection, shear force and bending moment diagram for a beam. So this is the same case. Okay, so you can follow the same procedure. Key point is 1 at the location 0, 0, 0, apply, and the second key point is number 2 at a distance of 1 meter, which is in SI unit. Okay, now join this 2 with the help of a line, lines, straight line. select this and select this. Okay. Once the modeling is complete, go to meshing. So I do not go to mesh attributes. Do not need to go to mesh attributes because I have only one cross section and only one material, right? So I can directly go to size control, panel size, lines, all lines, and let me divide it into say 200 elements. Right? So you can divide as you want, depending on your computer use, that is the memory and your processor speed. Right? So I'll just divide it into 200 elements and mesh lines. I'll select this line. I'll click on OK. Yeah, it's meshed. So now I have to go for loads. So directly instead of applying the loads, I have to change the analysis type first. So go to analysis type, new analysis. From static, change it to modal analysis. Click on OK. Once you click on OK, you can find here. Once you click on OK, you can find this option gets changes. And under the analysis option, and these are the algorithms which are used to solve the model. I'll leave it up to block length source, and I'm not going to disturb that. But I have to specify how much frequencies that I have to calculate. So number of modes to extract, which is the number of frequencies to extract 50, and number of frequencies to expand, which means in order to show the results, initially I have to extract the frequency, then I have to expand the frequency to show you the results. So in both the cases, I am going to give 50 because I have to calculate the 50 natural frequencies and I have to expand the 50 natural frequencies in order to show you the results, right? And I'll click on OK, and in this dialog box, leave everything as it is and click on OK. Now I'll set up my problem and I'll define the boundary condition. This is a cantilever beam. Initially I'm going to solve it as cantilever. So go to structural displacement on key points, select this leftmost key point, click on OK, and all degree of freedom is arrested and the displacement value is 0. And in ANSYS, if you do not give anything, it will automatically take it as 0, just for information. Okay. So that's all. In modal analysis, you do not need to give any force. So even though you know that the vibration will be excited only with the help of an initiating force, in ANSYS, you do not need to give any kind of initiating force to create the vibration. It will consider itself initiating force and it will automatically determine the vibrations for you, right? And so you do not need to give any force. Whatsoever force you will have, just neglect that. In modal analysis, you have to only draw the problem and define the state where it is fixed or boundary conditions, corresponding boundary condition, whether it is hinged or whether it is free on which end, right? Similar boundary condition has to be given and you have to directly analyze the problem. You have to solve the problem without giving any force values, right? So directly I solve the problem, solution, solve current colors, and I'll click on OK. Right, solution is done. Now let me see my results here. Okay, let me go to general post processor, click on result summary. You can see all the 50 natural frequencies, right? So starting with 40.819, right? And let me compare this value with that of my theoretical calculation. Okay, here it is. So my first frequency for cantilever is 40.929, right? So this very much matches with my ANSYS value, which is 40.819, which is a close match, right? So 40.929. My second frequency is in theoretical calculation. I have my second frequency 256.539. Here I have 252.86, which is also a closer match, right? Now, if I go on to the third frequency, which is 717.726, and the closer value to 717 is 726.27. As you can see, the frequency moves on higher. The difference between the theoretical answer and the calculated answer from the ANSYS is increasing, right? Here 40.81, I have 40.92. Here I have 256, here it is 252. Then here it is 717 in theoretical calculation, and in ANSYS I have 726, right? And next answer is going to be, and the error is going to be even higher, 1406. Here I have 1329. So you can see the error is very much huge. And finally, here I have 2324, and here I have 2178. That's the closer value that I have with my theoretical cancer. Took the model frequency, which is 2324. Here I have 2178, or the closer value is 2132. So only these two values are closer to 2324. As you can see, as we go on to the higher model frequencies, higher modes. So this is the fifth mode natural frequency of the cantilever beam. The error gets on increasing, right? That is due to the fact that these constant values which you can find here are determined experimentally, and lots of factors influence when you calculate this experimentally, right? And you can also theoretically, you can using ANSYS you can calculate n number of frequencies. The 50th frequency is 16464 hertz. But is it possible to achieve this natural frequency? Is another matter, different, totally different, right? You can't be able to achieve this high number of high frequency in real world scenario. Real world scenario will be able to only achieve very lower order frequencies, say first 5 or first 10 frequencies. If you achieve the 10th mode frequency, that would be a great achievement in real world scenario. But ANSYS gives you n number of frequencies. Right? Okay. Okay, just compare these values. Just compare the values that you get in the theoretical answer and which of the values closes very much closer to the value. Just compare that. Right? Just copy this value, copy all these 50 values, put it in a notepad, and file it in your manual. Right? But in order to calculate, compare with the theoretical answer, compare only the 5 values which are very much closer to the theoretical calculation from ANSYS. Right? So in order to see how the how my beam gets deflected for each and every frequencies, you don't need to see for all the 50 frequencies. Just see the 5 frequencies which matches very much closer to your theoretical answer, right? Let me see for the first frequency, 40.819. So in order to see that, go to read results, by pick, select the first frequency, read, close. Now plot your results, deform plus undeform, deform plus undeform, click on OK, right? So I think you can't pretty much see here because it is in the third dimension. Here you can see, right? Here you can see how it has deflected. So even you can even animate and see how it is going to vibrate, right? So just change it to sinusoidal, deform plus undeform, click on OK. Maybe I will just minimize this. Right. You can see how it is vibrating, right? So this is the first mode frequency, right? Just save this image, capture this image using plot control, write meta file, invert black or white, and save it to ANSYS. So for all the first 5 frequencies that matches with the theoretical answer, save this model image, right? Now let me go on to the second value, which is 252. So read results, by pick, select the 252. So this is the 2 values gets repeated. This is due to the fact that the same vibration, this happens in XZ plane, will happen in XY plane also, right? That's why you get the same values. Just ignore the repetitive values. Just go to the next value, which is 256. Read, close. Now let me go on to plot control, deform plus undeform. Select deform plus undeform, click on OK. Right here you can see how it is reflected. Now again go for plot control, you can see the vibration using the animation, click on OK. You can see how it is vibrating. See here you have 1 point and here you have the fixed point. These are the 2 points which does not vibrate. So that is why it is called as the second mode. You have 2 points which does not vibrate and remains in the mean position at all times. Hence that is why this is called as the second mode frequency, because 2 points, 2 modes are still available in the mean position, right? Okay. Again save this image and write meta file, invert white or black. Similarly, for all the 5 frequencies that matches closer to the ANSYS theoretical value, save this model mode shape images, right? Okay. So this is for a cantilever beam, right? So what if this is a fixed beam, right? I'll tell you how it will deflect for a simply supported beam later. Now I'll just show you. I'll directly solve the fixed beam, right? So this is my fixed beam, third case. So I have to arrest, already I have fixed here. Once, one more time I have to fix it here, right? Displacement on key point, I'll select the rightmost key point, I'll click on OK. On all degree of freedom, 0. Okay. Now this is a fixed beam because I have already fixed it here and I have done all the necessary things. I have changed the analysis type, I have given everything. Just I have to solve it once more. Right. Solution is done. Now let me go on to the general post processor. Right. Now let me go on to the general post processor result summary. Here you can find. So first frequency was 40. Here now it has changed to 255.91. Let me compare it with the theoretical answer, which is 260.194, and the first frequency is 255.91, which is a close match. Okay. Next I have 717.725. Next answer is 717. The closer answer is 690. and the third one, which is 1406.216, and here I have 1318.1. So this, 1318 or 1452. This is again one more close value to 131406. Then I have 2324.935, 2324.935. I have 2531.9, which is a close value. Then 3473.149, 3473. I have only 3042. That's the closer answer that I get. So as you can see, once you go on to the higher mode frequencies, the error gets even higher. Don't worry about it, right? This is normal for vibration problems, right? Just note down what are the values that you get in ANSYS. Don't worry about the error being large for the fifth mode, right? Okay, so this is for a fixed beam. Similarly, you can see the mode shapes and just save the mode shape image for the first 5 frequencies, which matches with the theoretical answer, right? Now, let me solve the same problem for a simply supported condition, right? Okay, now, so in order to do this again, I'll just let me change, let me delete the value here. Okay, now, so up to now, I have changed the analysis type, which I have done earlier. Now, I have changed the solution. Analysis type. I have already chosen mode, and I have already analysis option. I have already given as 50/50. Directly, I have to define my loads, define apply structural displacement on key points. Let me select the 2 end key points. So this is simply supported. So instead of all degree of freedom, the 3 translation, 2 rotation, and the out of plane rotation should be free, right? So click on OK. Now this is a simply supported condition. Just I have to solve it. Solution solve current LS and OK. Yes. Now you can find results somewhere. So values again is changed to some other values, which is 114. So 114.748. Here I get 114.33. A very close match. Next value is 458.994. Here I have 451.79. Okay, closer. Again 1033.46, 1033. Here I have 996.97. That's the closer value. And next is 1836.7, 1836. The closer answer is 1727.6. And then my close value is 2870. Here I have 2905, right? So as you can see here also, as you go on to the higher modes, the error gets higher. Don't worry about it. Just save all these frequencies, 50 frequencies, then compare the frequencies which matches with the theoretical answer, and only for those frequencies, save the mode shape, right? So this is all about modal frequency, right? So while doing modal frequency analysis, both in theoretical and in ANSYS, keep sure in mind that you give all the unit as SI unit, that is the length unit in meter and the mass unit in kg and force unit in Newton. So only that is the issue that you will have, and other than that, you can easily solve this problem and get it for your particular problems, right? So do not give any force. That is also important in modal analysis. Just solve the problem as it is, only by defining the end conditions and also the material properties and the friction properties. Right? So once again, let me see you in another video tutorial. The next video tutorial for harmonic frequency response analysis. We'll see that. So until then, signing off is Shankar. See you.